Hey guys, welcome to Safi Mixed. In this video, I want to derive relations for dynamical variables and hence for the trajectory of a particle under the condition of a time-dependent force. That is, I will consider the situation where the force F acting on a particle is time-dependent. F is equal to F of t. There are several practical problems in which the force is time dependent. For example, we know from the solution of Maxwell equations that the electric field is time dependent and is usually given by the form E equals E naught cos or sine k dot r minus omega t into vector. I would write the vector as E. Here you see that the electric field intensity of electromagnetic field is time dependent, and obviously when the electric field intensity is time dependent, then the force exerted by this electric field on a charged particle is also time dependent. Another very important example that we can even experimentally devise in our lab is a charge capacitor. These are the terminal plus and minus. If we connect this charge capacitor to a conductor or resistor, then the current starts flowing through the conductor. That is the free electrons inside the conductor experience force due to the electric field inside the electric field established by the charge capacitor. And this force is, since the electric field with the passage of time decreases as the current passes through the conductor, and the force experienced by the charged particle is also constantly changing with time. So the force experienced by the electrons inside the conductor is also a function of time. There are several other examples, practical examples, in which the force depends on time. Here I want to and this is not only related to electric field, there are several mechanical examples in which force depends on charge, in which force depends on time. So in this video, I want to develop a generalized formalism for finding the trajectory and dynamical variable of particle experience force Ft. To this end, from one of the differential forms of Newton's second law, I can write dv over dt equals 1 divided by m f of t. So instead of solving this equation in vector form, I want to reduce this to a scalar form by considering only one-dimensional motion. In that case, I prefer to write this equation in the form of x component of velocity would be equal to 1 divided by m f of xt. And writing this in one dimension, I drop the vector notation from the vectors v and f. So this is now a scalar equation, and you can deal with it very easily. And to further simplify and my mathematical notation, I even drop the x with it, but we presume that we are dealing with the x component. And the formalism that I developed can straightforwardly be applied to the y and z components. And from the results of the three components, we can then write down the vector equation for 3 dimensions for the dynamical variables. So in order to solve this one equation, the general strategy is to separate this in variables. So that's why I write this into dv equals 1 divided by m f of t into dt. Now we can integrate this equation if we know about the initial condition on the velocity of the particle, and I suppose that the initial velocity is v naught at time t naught and is similarly v at time t. So I can integrate this equation by writing v naught, v dv equals 1 divided by m. I'm writing m out of the integral because I consider that the mass of the particle is conserved, that the mass of the particle is constant. Therefore, I write this T naught T f t prime dt prime. So now I can straightforwardly integrate the left side of the equation to get v from v naught to v equals 1 divided by m integral from t naught to t f t prime dt prime. I cannot integrate this equation so far as I don't know the exact form of the force, so I leave this as this is. And then from this I can write that if I substitute the limit, that v minus v naught equals 1 divided by m integral from t naught to t ft prime into dt prime. Or I can further write this in the form v naught plus 1 divided by m integral from t naught to t ft prime dt prime. This equation gives the velocity at any time t, and we see that this is in fact a general relation or a general solution for the velocity of particle under the action of time-dependent force. I call it general because we don't have a numerical value to v naught. This equation is applicable for all values of v naught, so it is a general relation. And you see, the velocity of the particle depends on two terms on the right side. Number first, the initial velocity. For every different value of v naught, we will get a different value of v. And similarly, the integral of time-dependent force over time, this gives another effect of the particle. And in fact, it is this term that defines the increase or decrease in velocity, because this is time-dependent part, this is independent of time, and we call v naught sometimes the integration of the constant of integration. Now, since the velocity depends on time, as you see from here, therefore I can express the left side of this equation in terms of v equals dx over dt, where x is time dependent, right? Because v is time dependent, we see that from this integral part, this v depends on time, that v is a function of time. So when v is a function of time, we can write that in terms of the derivative of position. And if I use this value for velocity at this position, I can write this as d x of t over dt equals v naught plus 1 divided by m integral from t naught to t ft prime dt prime. And again, multiplying each term with dt, I can separate the variables, and to do that I write this equation in the form dx. I'm dropping the function x, however it is understood that dx depends on time, and I write this as v naught dt plus 1 divided by m. I enclose this inside brackets and write this as t naught t ft prime dt prime, the whole multiplied with dt. And if again I know about the initial condition on position, that is, I know the initial value of position at time t naught, I can find the trajectory or the position at any time t. And I suppose that initially the position of the particle is x naught at time t equals t naught. Then I can integrate this equation and can write this as in the form dx from x naught to x equals, since v naught is a constant, this is constant of integration, or this is the initial velocity, therefore it is a constant, and I can write this as v naught integral t naught to t dt prime plus 1 divided by m. I'm taking the m out of this bracket. It doesn't make any difference because this is also constant. And then I integrated from t naught to t, and I put this inside another bracket, and I can remove this bracket. It doesn't need to be written over here. And I put this inside the bracket, and I write t naught to t ft prime dt prime integrated with dt double prime. So in fact we have two integrals in the last term, one for t prime and the other for dt double prime. And again, this equation just gives me this part just gives me t minus t naught, so I can write, and this gives me x minus x naught, so I just directly put the values x minus x naught v naught times t minus t naught, and then plus the last term 1 divided by m integral from t naught to t, then integral from t naught to t ft prime dt prime, the whole multiplied with dt double prime. And I can rewrite this in the form, I remove these things, I don't need them anymore, so I can rewrite this as x equals x naught plus v naught, and I can replace this t minus t naught with the interval either delta t or I just write it t, and plus 1 divided by m into integral from t naught to t, and then integral from t naught to t ft prime dt prime into dt double prime. I should put, yeah, that's true. Okay, now again you see there the position depends on time, a time dependency in this term, a time dependency in this term. So the position of the particle is time dependent. In other words, the trajectory of particle is changing constantly with time, and that time dependency in fact is more obvious from here. What is the form of the force would just change the trajectory of the particle, because this part is, in fact these two terms gives a straight line, but so far as we don't know about the exact form of the force, we can't say anything about the exact trajectory of the particle. However, if the force is constant, then we will get obviously there are two integrals, we would get a quadratic terms from here, and if the force is sinusoidal, then of course we will get another form of the particle, or if it is exponential increase or decrease like in the case of capacitor, we would get another form of the trajectory of the particle. Nevertheless, the main form of the trajectory depends on this term, and there involves two integrals, so the two integral will make this term either quadratic or sinusoidal, whichever form of the force is. That's possible only with the exact form of the force. So we can solve different problem of experimental importance by using this form to find the trajectory or position of the particle, and then this form to find the velocity of the particle. Or in other words, we first find the position of this particle if we know about the exact form of the force, and then differentiate it as per this one equation to get the velocity of the particle. This one equation, we differentiate the final position, which is time dependent, with respect to this one equation to find the velocity. So we can go both way, either to find the velocity from this one equation and then use the velocity in this one equation to find the position, or to first find the position from this one equation and then differentiate according to this one equation to find the velocity. So these equations, these two equations, this one equation and this one equation, in fact gives the dynamical variable of a particle under the condition of time dependent force. And thanks for watching.